I am pretty sure every video which you have watched around distributed training would stop around the same place. Data parallelism is about copying models. Pipeline parallelism is about breaking your model into layers and moving forward with that. You might be happy that you have learned a lot, you like the animations and everything, but still you won't be able to answer one of the most important questions. How far will your system scale before half of your GPU or half of your flops are sitting idle? With your current hardware, how far can you scale your batch size? Or with how many GPUs can you train with? Hello everyone, I'm Aditya Ghai, and in the entirety of this video, we are going to try to answer these hard but trivial distributed training problems. I'll cover LLM math, sharding fundamentals, communication primitives, and the rooflines, like how long does it take for an AllGather or an AllReduce. If these sound like buzzwords to you as of now, do not worry, we'll cover them deeply in the video. And of course, the video is about distributed training. We'll go through pure data parallelism, FSDP, tensor parallelism, pipeline parallelism techniques like DualPipe, which the latest DeepSeek models are trained on. I'll try to deeply go inside every method, like their entire forward pass, their backward pass, like the roofline analysis, when do they become communication bound, their pros and cons. So let's get started. A short note before getting into the video, what this video is and what it isn't. It's not an LLM introduction course. We will not be discussing about attention, neural networks, or what is a forward pass or backward pass. I hope you understand those fundamentals. Before starting any new section, I'll definitely let you know and link really good resources in the description of what exactly you need to know before this section so that you can grasp all the concepts. So do not worry about that. How have I made this video? I have read loads of blogs. I'll try to link as many, but that list won't be exhaustive. And one of the most important resources would be the Jack scaling book. Go through it as well. But as far as distributed training is concerned, for both TPUs and considering GPUs, any sort of accelerator, I'll try to be as generalizable in the entirety of this video. Now we'll get started with the most important fundamental in distributed training, that is sharding. You're breaking something into shards. What are LLM operations? Whatever you do in the entirety of LLMs is just matrix multiplications. Everything is matrix multiplication. These weights which you call, there are millions of weights inside an LLM. These are just matrices. From your high school, you must remember, let's say this is a 2D matrix like this. This is a 5 cross 5 matrix. I number of rows, j number of columns. Right now I and j are 5 cross 5. So the problem of distributed training now shifts down to a very simple problem. How do I multiply two matrices or multiple matrices given that the weights are on different chips? The parts of a matrix are on different chips. If they were on the same chip, A and B, let's say I wanna do a dot product of A with B. If it was like M cross N matrix and I wanna multiply with a N cross P matrix, this is the contracting dimension, I'll get a new matrix M cross P. Suppose some part of this Mn matrix was in GPU 0, some part of it was in GPU 1. That is everything around distributed training. You just want to understand how do you multiply these and get the results. So we are on the Jack scaling book on the sharding section. Why are we here and not on the whiteboard? Because the animations here and images here are more intuitive. They are easier for me to explain. Whenever I feel that I need to move to the whiteboard to explain some math, hard math, then I'll definitely do that. We are here to firstly understand the partitioning notation. Why are we sharding entirely? Let's again answer that question, because our arrays don't fit on the HBM of a single chip. HBM is high bandwidth memory. You can think of it as simply RAM. The RAM of your chip is just not big enough for very large matrices. So this is an matrix A, I rows, J columns. Now we'll talk about mesh. A mesh is like a 2D or 3D place where all your chips are put in. When I say X2 and Y2, I mean to say that across the X mesh axis and the Y mesh axis, I have respectively 2 and 2 chips. It is not very necessary that the X axis should be on the horizontal line. It can be on the vertical line as per this article as well. To make this easier to understand about sharding, let's look into an easier image. Okay, let's look into this. I rows, J columns, 4 cross 4 matrix, 0 index examples. I have 4 devices. Okay, suppose I want to put my entire matrix Aij
on these 4 devices, complete matrix, nothing is being sharded. So every let's say chip has 4 cross 4 matrix. That is very cool. Now if I want to shard it IXJ, so what do I mean by that? I want to shard my I rows, the rows across the X mesh axis, and the column should remain totally normal. So the columns are always normal here, but what have we done here? Across the X mesh axis, I have divided or sharded my matrix. So how is that going to look like? 4 cross 4 matrix, I want to shard that across this, the vertical line. How do I do that equally? I just do that to 2 rows, 2 rows, 4 rows total, so 2, 2 equally partitioned. And across the Y mesh axis, everything is same because nothing is being sharded there. Another example would be IXJY. Across the X mesh axis, I want to shard my rows. Across the Y mesh axis, I want to shard my columns. This would have looked exactly like this if we had all the columns same, only J, but we had JY here. So the columns are also being sharded here. To understand this deeply, pause this video here and just think of this example for your 4 devices, 4 cross 4 matrix, and try to write down on a piece of paper how the shape would actually look like. So these are mostly cases we have already discussed. If we'll think about this one, I want to shard my rows across the Y mesh axis. We have done that. 0 and 1 row here, 2 and 3 row here, and that is entirely replicated here. When I say I want to a partition or shard across both X and Y, my rows on both X and Y mesh axes, then I do that in this way: first row, second row, third row, fourth row. So does X and Y, what if it was written YX and not XY? Would that have changed things? Yes, that would have. The order would have been changed. When I say X mesh axis first, the first row, second row, third, fourth. When I say Y mesh axis first, this is the direction of the Y mesh axis. So first row, second row, third row, fourth row.
I hope you understood the sharding notations. You actually opened your notebook and wrote down the examples which I showed you. Another short example so that we can confirm that we are clear with the sharding notations and we can move forward. Aij, I rows, j columns, this is my matrix, 6 cross 3. I want to shard it, my rows across the y axis, y mesh axis. And I have already shown you that x axis is down, so y is this axis. If I want to shard my rows, how do I shard them? Very easily. I want to equally shard them. So I'll give just 2 rows to each accelerator. Now let's move forward. Let's get started with computation with sharded arrays. As I said, LLMs are just matrix multiplications. If your matrices are sharded on different devices, we just want to learn how do we multiply them. There would be entirely 4 cases, and in these we'll also discuss about communication primitives. So let's get into it. Case 1 states that neither of the multiplicants have the contracting dimension being sharded. What is the contracting dimension here? J, because it's going to get vanished to give me this dot product sharded matrix C. I do not have to do any sort of communication. I don't have to completely build a matrix on every GPU. In the states which they are, I can directly multiply or have a dot product with them. Think of it this way. In the X mesh axis, I have the I rows being sharded. So if it was 6 rows, I have like 2 rows, given that I had 3 accelerators. Try to visualize this with me. I have complete rows of A, and along the Y mesh axis, I have the columns being sharded. In a dot product or matrix multiplication, I am multiplying rows by columns. It's a straightforward operation, and I will get this sharded C matrix. Now case 2 is one of the multiplicand have the contracting dimension being sharded. The contracting dimension is J because it's going to get vanished. So here in this case, one of the matrix has to have the contracting dimension being sharded in any mesh axis, be it Y, Z, or it could have been this one as well, but only one of has to be sharded. Now the problem here is, consider this case. This is my complete row of A, but the columns are being sharded. So I have some chunks of my row on each individual GPU or any sort of accelerator. This is a complete matrix. It's going to be there completely. I want to multiply my rows with these columns, but my rows are not complete. So I cannot do this operation, right? So the only technique which I can think of to actually multiply these two matrices would be to get this matrix completely on every GPU. If there was any sort of operation that could convert this into the complete matrix on every GPU, then I can simply multiply them, their complete matrices, and that would give me the resultant C matrix. And that operation is called an AllGather. Let's get into it. So what is an AllGather? It's one of the most core and primitive MPIs. It's like a code of conduct for how do systems communicate in a distributed setting. Fundamentally, AllGather would remove the shardings along a particular axis. So you have, let's say, 5 devices. I'll go with 4. You have some shards of a matrix, and I know that if you could combine all these 4 shards, I would have the complete matrix. So the intuition of an AllGather is it will ask every device to move its data until it gets the entire data to build A. That's what an AllGather does. From case 2, we understood that if we have a multiplicand with a sharded contracting dimension, we must perform an AllGather first, and only then we will be able to multiply. There's another method called AllReduce, we'll discuss that later, but for now, we understood that the first step in such a case would be to do an AllGather. Now we have complete matrices on every chip, and we can just multiply them. But how long does an AllGather take? Now let's discuss that. Now we are discussing the time requirements for an AllGather operation. These circles here are actual chips, TPUs or GPUs, what kind of accelerator you are using. And these lines are physical connections. We call them ICI links or inter-chip interconnect links. These are actual physical connections between two chips. So they have a bandwidth, how fast they can move the data. We represent that with WICI, the amount of bytes I can move per unit time from these physical connections. The total byte size of my array, when I wrote Aij, this is a matrix, right? I want to represent that in like BF16, like FP32. So that full size of bytes is V. There are X number of shards, that means there are X number of devices. So each local shard, how much storage of this V, how much part of this V is stored on every local accelerator? We can think of it this way. I haven't discussed this before. When I write something like this, the local size of each shard would be I by X, J. Because I'm sharding a complete matrix, okay? So there should be some part of it on each accelerator. If I would have written A, I, X, Y, J, the local size would be I, X, Y, J. It's intuitive. You can think of it this way. If J would have been like, let's say, A, I, J, Y, the local would be I, J, Y, Y. The columns are being sharded. So suppose there were 10 columns on the entire matrix. I had 5 GPUs with myself, so 10 by 5. So every device would be having 2 columns. In an AllGather, I want to move all my shards to every TPU or GPU. Suppose I start from here. The maximum distance I have to cover, given that this is a linear line, this is the furthest distance. 1 hop, 2 hop, 3 hop, 4 hop. So X minus 1 hops I need to do. Another case, if this were a ring, if this was a ring in TPU architecture, we can have bidirectional bandwidth. That suggests I can not only just move in one direction, but I can move in both the directions. So what's the furthest points? This and this? No, because these are not directly connected. In 1 hop I can reach here. These would be the farthest points. So in 1 hop I move this direction and I reach this point. Then from here I move in this direction and this direction, I reach all the TPUs. So I exactly have to do 2 hops. That suggests when we are in a bidirectional bandwidth setting, I have to do x by 2 hops. Now the next question is, when I do a single hop, how much data do I move? We'll be considering the bidirectional scenario that data can move in both the directions. Suppose I am on this device. I want to move my local shards, that is v by x size, in both these directions. So in a single hop, I move 2 into v by x bytes. We are fine with that? What if I divide this with WICI, the amount of bytes I can move per second? And I divide that with WICI. This is the time for each hop. Why? Do some dimensional analysis. Bytes divided by bytes upon seconds, that gives me seconds. That's a unit of time. That gives me the total time required for each and individual hop. Now, how many hops do I have to do such that each shard reaches to all the TPUs? As I said, this is a bidirectional setting. I can move data in both the directions. Then I have to do x by 2 hops. So total time for an AllGather would be, the 2 gets cancelled, the x gets cancelled, so it becomes v by WIC. So for an AllGather operation, given that we want to gather the complete size of the array is v and we have the bidirectional bandwidth as WICI, this is the total time. The cool thing about this is, if you had 100 devices lined up on a certain mesh axis, or even 1000, the time for an AllGather would not depend on the number of devices. But there is a catch to this. If your array which you are moving is really small, the total time won't be this. Why? Because the hardware has overhead around 1 microsecond when we are considering this specific hardware. So the minimum time you can take to move data over this ICI, this physical connection of links, ICI links, is 1 microsecond. So if you take, for example, when this scenario can come up, the unidirectional bandwidth for this is around this size of bytes per second. So this is the minimum time we have to take in. So if I multiply this with 1 microsecond, I get around the value to be 45 kbs. If the data you are moving is less than this part, we get latency bound. If the time which is coming is like, let's say, like picosecond or like 0.001 microseconds, then like the minimum time would still have this overhead. So T total should be the maximum of the T minimum for each hop. So I want to do x by 2 hops and v by WICI. This is something you can keep in mind. One more scenario when we are discussing about AllGathers. Till now I have discussed only about a single mesh axis. Suppose this was a 2D structure. When we are considering TPUs, we can have 2D and 3D toruses as well. Now think about this, when I only had a single mesh axis, my bidirectional bandwidth was able to move in 2 directions, right? I had 2 physical links connecting a single device. Consider this device. Now this has 4 directions to move. So my effective bidirectional bandwidth would become twice of WICI because I have 2 more directions to move into, 2 more physical links. If this was a 3D torus, I can move out of this boat and I can move inside of this boat. This would have become 3 times of WICI, right? My bandwidth is increasing, so the time would decrease in such a case. So my T total would now become the max of, I still have to think about the overhead, T minimum into x star by 2. I want to do x star by 2 hops. I'll tell what x star is, comma, v by WICI into n axis. N is either 2 or 3. With TPUs you can build 2D or 3D toruses because your effective bandwidth would double or triple considering you are in a 2D or 3D structure. What is x star? This we were considering here the maximum number of hops I want to reach So we have to consider all the mesh axes along all these x, y, z mesh axes. I want to find the maximum distance. So like if we had I'll consider the maximum distance now along this mesh axis and not this. Now we come to case 3, where both the multiplicants have a sharded contracting dimension. For A, the columns are being sharded across the x mesh axis and the rows of B are being sharded also along the x mesh axis. The cool thing about this, we can actually multiply them and we'll have partial sums on each device, and we just need to sum those sums up to get this dot product. Okay, I hope this is totally not clear. We'll do an actual numerical example to understand this. We'll learn about 2 more communication primitives. One would be AllReduce and one would be ReduceScatter. So let's get into the numerical part. So a numerical example should make things clear. 2 rows, 4 columns, 4 rows, 2 columns, A and B. This is how they're going to look like. Can make this look a little bit better. How's this? 1 0 0 1 1 1 and 2 0. The final output CIK would be a 2 cross 2 matrix, 2 cross 4, 4 cross 2, contracting dimension vanishes, 2 cross 2, right? It's going to be I hope my calculations are right. Yep, they are right. If we are doing this on a single GPU, this is the entire results. We can multiply them at the same time. Nothing is being sharded. Suppose I have 2 devices along my X mesh axis. I can take any arbitrary direction. I could have taken this as well. I want my X mesh axis to be in this direction as of now. My contracting dimensions are sharded. So the columns are being sharded for A and the rows are being sharded for B. This is my device 0. This is my device 1. I would appreciate if you would stop the video and actually try to write how the local shapes of both these matrices would look on device 0 and device 1. Otherwise, I'll continue now. So I have 2 columns on this device, 2 columns of A in this device, right? We want to shard the columns. So the local shape of A would be 1, 2, 5, 6. And on this device, it would be 3, 4, 7, 8, right? For B, what I want to do, I want to shard the rows. So there are 4 rows. I have 2 devices, 4 by 2, 2 rows on the first device, 2 rows on the second device. 1, 0, 0, 1 and 1, 1, 2, 0. The good part now, the result which I am going to get from here would be a 2 cross 2 matrix, and here as well a 2 cross 2 matrix, which is actually the shape of our final matrix. Let's multiply. Right? So these are the 2 partial sums of C which I have got. Why do I say that? Try to do, like, think of this, how do I make from these 2 partial products into this C, the final matrix here? What can I do? Just think a little bit on that part. Okay, the answer is you do an element-wise sum of these 2 and you get a CIK. 1, 12, 5, 28 and 30. Now the condition in which we are in would be represented something like this. Denotes a local dot product and show that C is unreduced across the X mesh axis. We have partial sums here. From this, we can move in 2 directions to achieve the complete matrix on every individual GPU. One is ReduceScatter and the other one is ReduceAll, which is actually ReduceAll is ReduceScatter plus an AllGather. We'll get into the details of these. First, let's discuss about ReduceScatter. So this is what we are trying to do with the ReduceScatter. This unreduced partial sum of Cik, I want to move that in such a way that like we are summed up, but we get sharded columns here Cik. So if I were to perform ReduceScatter x over k, then this on this device I would be having 12,28, and on this device I want to be having 5,13. My columns are being sharded. So what's happening actually? I'm taking my first column and moving around, and this is so every device is moving their individual shards in both the directions until it reaches on all the devices across that specific mesh axis. So if there were 4 devices, I would take this column and move ahead, and every other device would be moving their columns. Thus, we get a sharded like a product or sharded CIKX matrix finally when we do a ReduceScatter. So how similar is ReduceScatter to an AllGather? We are actually doing something very similar. Every device is actually moving its shards. In AllGather, we were actually retaining those shards, but here we are doing sums of those. So the time would be almost equal to AllGather, just there would be an overhead of actually adding those shards. Now let me tell you about ReduceAll. What is that going to do? From this unreduced sum, I'm directly going to get the complete matrix Cik on every device. This is a communication technique, not a primitive. I'll tell you why this is not a primitive method. Because what do I want to do here? You can treat ReduceAll as ReduceScatter plus an AllGather. Thus, it's not a primitive. These are primitive methods. I can just combine 2 methods to make a new method, right? What's happening here? After you do a ReduceScatter, you get these sharded Cik matrix being sharded along the columns. What do I want to do next? Suppose there were 7 devices, each one had a single column. I want every TPU to share its keep sharing its shards until it has all the shards. It has a complete matrix. That's what an AllGather does. So after ReduceScatter, if you do an AllGather, then you finally get your complete matrix. That's how you write about or tell about ReduceAll. So the time taken by ReduceAll, these take equal time. Thus, twice the time of an AllGather or twice the time of ReduceScatter is being taken by ReduceAll operation. Now let's get into the final case, case 4. Both the multiplicants have a non-contracting dimension being sharded across the same mesh axis. Non-contracting dimensions means I here and k here. What do I want to do with them? I want them to be sharded across the same mesh axis, right? X here is same, would have been y or something else as well. The output of this would be ix comma kx. Now think about this. Is that even possible? This is not physically possible. Your rows and columns being sharded across the same mesh axis. Thus, this is not possible. So how do we move forward with this case? You either AllGather this or you AllGather this. If you would AllGather this, then you would have the complete A matrix on every device. Thus, your final sum would be sharded across the columns. If you would have AllGathered this, then your B matrix would have been complete on every device. A would be sharded across that axis. Then your C would look like Ix comma K. Now you can think about this beforehand, what further computations you want to do with your dot product C matrix. Thus you could have your rows being sharded or columns being sharded. This ends our case for sharded matrix multiplication. All these 4 cases gives out all the combinations possible. Now let's move on to the next topic of one more communication primitive called AllToAll. Now we come to the final communication primitive, that is AllToAll. What are we trying to achieve here? You can see like when I pass this sharded matrix along the rows to an AllToAll function, what it does is that now the sharding has been changed to the columns. So in practice, we are doing a sharded transposition here. It's generally not required when we are doing sharded matrix multiplications, but you will get to the use of these when we are discussing about mixture of experts or MOEs. Now I want you to do this by hand. Suppose you have a matrix 5 cross 5, 5 rows, 5 columns, and you have 5 devices. Suppose it is sharded in this way only along the X mesh axis. So each device has a single row. Now I want to perform an all-to-all. Each row now should become a column of that specific matrix. So one column on each device. Try to do that on your own. Consider, like, if it's easier, you can do just a unidirectional bandwidth. So there's a single direction your data can move into, or you can try in both directions as well. Try to figure out, the first thing you're going to notice is the data which is being moved is not uniform. Like in an AllGather, you are directly moving the shards, like the complete shards from one device to the another. But here it's not the same case. You sometimes are moving a larger part of the specific shard and sometimes moving a smaller chunk. So now like you will think about one thing, the time taken for all-to-all, because it's a communication primitive, we should understand that whenever we are using this, how much time does it take? If you want to remember this as a fact, it takes 1/4 the time of an AllGather. But of course, we are going to not stop here. We are going to get to the derivation. How do we get here? So let's get into it. Now we're going to figure out time for an all-to-all communication primitive. As I suggested before, each hop is not moving equal amounts of data, right? The amount of bytes being moved is not equal, it's changing, because this is a type of communication. It's not an AllGather where exactly same amounts of data would be moving. So we want to find out, first thing, the average hops a byte would take. Okay, there would be two methods. I'm gonna tell you how do we derive this final answer. The first one would be easier to grasp. Suppose I have a ring. So here we have bidirectional bandwidth. I can move the data in both directions. I have n devices. So for a target and source pair, any target, any source, the minimum distance would be either k or n minus k, right? So for all sorts of source and targets, I want to find out the minimum distance. Thus, I can average over this to get average how much a single byte has to move, how many hops a single byte has to do. So that would be something like, I want to average it out for all the devices. Averaging the minimum distance from each device. So this actually would give me what? The average distance or the average number of hops a single byte has to take. So how much would k move? To n minus 1, right? We would start with something like, there would be some amount of data, like when I'm making from a row to a column, there is a single point of data which should be on my device, so the distance would be 0. And the next one would be like the maximum distance I can cover, because this is a ring, would be the circumference, that would be n by 2. Try to open this out, k0, and the minimum would be this. I'll move to something like n by 2. Then what's going to happen? This series is first increasing, then it's going to start to decrease and move again to 1. So these are two arithmetic progressions. Try to write this down on a notebook, and when you will try to solve them with sum of an AP, it's n by 2, 2a plus n minus 1d, right? Try to solve these two. You'll get something like n by 4. So a byte has to travel, for an all-to-all communication primitive, a byte of data has to travel on an average n by 4 number of hops. That is the first thing we derive here. So we found out that average hops per byte is n by 4 when we are discussing about communication primitive all-to-all. Now I want to find out what's the work done by the entire system? Right, there are n physical links. If a single byte has to do these many hops, what's the entire system going to do? One byte takes n by 4 hops. I have to totally move v bytes. Thus, the total byte hops or work which I am going to perform would be v into n by 4. Right? This is the total work which is being performed. Now think of this. What's the work done by each individual link? Per link work would be the total work divided by the number of links. You can also call this per link load. That would be v by 4. A single link is doing this much work. Thus, I can finally say the time for an AllToAll would be this total work divided by the total bandwidth which I can perform. So in a single ring condition, I have a bidirectional bandwidth. This would be the final answer. If you'll compare this with something like an AllGather, when we are in a single axis, single mesh axis, this is the factor of 1 by 4. Because an AllGather is just v by wici. Now this is not the best method to finally find out this answer. A better method would be considering 3 mesh axes, because in TPU structures you can build a 3D torus, and this is only considering a single mesh axis. So let's discuss the next method. Please do not be intimidated by this diagram. It's a very simple structure. Let me explain. There are 6 devices here, and this is just a wraparound connection. So this is for illustrative purposes. For 6 devices, I don't think TPUs would allow a wraparound connection, but believe me, for this image, we have wraparound connections. So if I were to think of this as a mesh, right, I'm considering this as the x-axis and this as the y-mesh axis. Could have taken the other way as well, but this is fine. This is my cross section, okay? This is a cross section. Now, as I said, we are trying to figure out the time it takes for an all-to-all communication primitive. How are we going to get there? We'll try to figure out one thing: the amount of data which is going to move from past this cross section, like in one direction. Let's say we are not considering both directions. In one direction, how much data would cross this path, and the bandwidth across this cross section. If I'll divide with that, I get the time. So we are trying to figure out something like time for an all-to-all would be data moving across the cross section divided by the cross section bandwidth. Fine, we are going to figure out both of these together. Now the entire size of my matrix is V. If I have divided this from between, there are 12 devices, 6 here. So uniformly I would have V by 2 bytes of data on either sides. Now for an all-to-all communication primitive, each device would be sending half of its data to the other side. Now let's try to figure this one out. Suppose I had this one row here consisting of 6 elements. One element would stay here, one would go here, one would go here, and the other 3 would go past, because they have to reach these 3 devices. So they will cross this cross section. 3 would cross, total were 6, and for each device, half would come. Each device is sending half of its data to the other side. We have uniformly divided the number of devices. So the amount of data moving from this side would be V by 2 into half, because the total data is half I am moving on the other direction. So the total data crossing this cross section in both directions, so like from this direction V by 4 data would go, from this direction to this direction V by 4 data would go. We have figured this one. Let me clear this up a little bit, then we'll discuss about this. So we figured out how much data is going to move across the cross section in one direction, that was V by 4. Now we are trying to figure out the one directional bandwidth considering the bottleneck. Okay, what is the bottleneck here? I made a cross section here. To divide these two equally, I could have also made a cross section here as well, right? But that won't be a bottleneck considering bandwidth. Why? Here I have 1, 2, 3, 4 links passing across this cross section. Okay, if I would have made a cut here, 1, 2, 3, 4, 5, 6 links would be passing. So I won't be bottlenecked here. Why? Because I have more physical links to pass on my data. My overall bandwidth has more time or more space to move. The data would have remained the same. V by 4 would be crossing this cross section or either this or this. That's not a problem. But I want to find the bottleneck because that's where I have to find out the maximum time for an all-to-all communication primitive. So across the longest mesh axis, I have like 6 devices. Total devices are 12. The plane perpendicular to the longest mesh axis would be the place where there would be bottlenecks, because this cross section would be squeezed in minimum number of physical links. How I want to calculate how much data moves in one direction. So if I was considering my bidirectional bandwidth, like suppose from this device, I would be having twice of what I am trying to figure out as of now. I'm trying to figure out just this data which can move. So I will think of this as my bidirectional bandwidth divided by 2, because I am considering only one direction movement here. Now I want to figure out how many links are being passed from this the most squeezed in cross section. This would be n by m. M is this mesh axis. Total number of devices n. Now I have wraparound connections as well. So twice of that. So here are the number of links across this cross section. What kind of cross section is this? The bottleneck one or the most squeezed one. Now the final question, what's the unidirectional bandwidth across this? So how many links do I have? I just multiply that with the unidirectional bandwidth. I get NWICI by n. So as I said in the starting, the time for an all-to-all communication primitive would be data crossing one way and one-way bandwidth across the cross section which bottlenecks you. We calculated both V by 4 and WICI by n. So this turns out to be where m is the length of the longest mesh axis, because along like the perpendicular from the longest mesh axis is where would be the bottleneck. So you can think of one thing from here. For an all-to-all, a square shape would be like better, like considering this is like really bad for you, a square shape would be like almost the best. And n is the total number of devices. Thus, this is the best formula considering any number of mesh axes. We can only have 3 as of now due to physical constraints. Thus, we conclude all-to-all communication primitive. Before moving on to the parallelism techniques, there is one last thing I want to discuss. That is, AllGather and ReduceScatter are transposes of each other. Now, why should we even learn about this? Why does it matter? Because it's going to come up in like further times whenever I'm going to discuss any parallelism technique. Because in the forward pass, when I'm doing an AllGather, in the backward pass, for that same step, for those gradient calculations, I'm going to be using a ReduceScatter. Why does this come up? We'll take a look at that time as well. But try to understand a few things here. An AllGather operation is like a broadcast. What are we doing in an AllGather? There are shards on a particular device. I want to send or copy that shard to all the devices. That's a broadcast operation. What do I do when I'm in a ReduceScatter type of situation? I have partial sums on all the devices. I try to sum up those sums and take that summed up shard to the required device. So I'm summing up and I'm taking that specific shard. So it's like a reduce type operation. So generalizing this, a broadcast and a reduce type operation are transposes of each other. In all the parallelism techniques which I'm going to discuss in the video, this is will be a common pattern. Suppose in the forward pass, I have an AllGather. In that specific step, when I'm going to be doing the back propagation, you're gonna see a reduce operation. Why is that gonna happen? Let me tell you with an example. Let's say I'm doing an element-wise addition of these two matrices. This is 6, 4, 6 rows, 4 columns. This is 1, 4, 1 row, 4 columns. This directly cannot take place, right? This has 6 rows, this is just a single row. What PyTorch would internally do, it's gonna broadcast this 6 times. So this single element is now broadcasted 6 times. And then I can perform my addition. Suppose this was an operation in the forward pass. What's happening? I have this single node of B. Now it has 6 branches because it was broadcasted 6 times, and it could have happened for n number of times. I had n branches coming out in the forward pass. In the backward pass, when I'll be calculating gradients for this node, what's going to happen? I'll be calculating gradients for all the branches and summing them up. This partial sum operation would be reduce operation. And when I did this specifically, this was a broadcast operation or something very similar to AllGather. For this derivation, I'll go by the conventions of the Jack scaling book. This is how they write the broadcast: U Kronecker product with identity matrix of size n cross n. What's U? We'll get to that. Kronecker product, we'll get to that. Let's start with something more simple. In is a identity matrix. If I write I3, that means all diagonals 1, size 3 cross 3. Other elements 0. You are fine with the identity matrix. Next is, what is U? Now U would be a column vector of required size and its elements would always be 1. So U belongs to, so it's a column vector with P real entries. So all elements have to be 1. So if I write this belongs to something like R3, the elements would be for a general matrix. General column vector would be this. For U, those would be fine. Now, what's this? Is this a matrix multiplication operation or this is something else? Kronecker product is used to, let's say, multiply two matrices which do not have the same contracted dimensions. Suppose I do something like this. This is M cross N, this is Q cross R. So you cannot do a dot product. So for this, we call this the outer product. We do a Kronecker product. How it's going to look like? For each element of A from the first matrix, let's say this is the first element, I'm going to multiply the entire matrix B. This is the Kronecker product. This is regarded as a broadcast operation. Let's broadcast on a very simple case now. Now I have P equals to 2. P is the number of devices. I have 2 devices along a mesh axis, and N equals to 2. That means the size of my shards. So my shard X would look something like x1, x2 because my size is 2. How would U look like? As I said, U belong to, this should be a column vector with P real elements. Okay, P equals to 2, so U would be great. What about this? N equals to 2. Fine, we know this. Let's do the Kronecker product. For each element, I want to multiply the entire matrix I2. So the Kronecker product would look something like this multiplied by entirely this 1 0 0 1, and this multiplied by this 1 0 0 1. Now try to multiply this with your shards. Now for this specific case with 2 devices and the size of each shards as 2, we finally got this as the U Kronecker product IN, this value. Now I'm trying to do a broadcast. As I said, when you get this value, you multiply this with your shards. This is a normal dot product, okay? As you see, like this is a 4 cross 2 matrix, this is a 2 cross 1 matrix. So the final product should come out to be 4 cross 1. Now, how do you read this? The first two elements would be for device 0 and the other two would be for device 1. We have successfully performed a broadcast. Now let us talk about the reduce operation. We already know that the transpose of a broadcast would be the reduce, right? So why not do that? The transpose would move to these individual elements. Try to build a few identity matrices and try to do a transpose of those columns to rows, rows to columns, right? This would remain the same. So finally, this would be your reduce operation. So before actually showing you an example with the reduce operation, first thing we should try to sum up what did a ReduceScatter actually do. Suppose I had these partial sums. I have two devices, device 0, device 1. I have y1, y2 and y3, y4. I have local partial sums on each device. With a ReduceScatter, what I want to do, I want to go to individual devices. I want to sum those partial sums and take that specific overall sum to the required device. So the final output would, after a timestamp, when we have done a reduce operation, this is done, then this should look something like y1 plus y3. The partial sums are on the required or designated devices, and y2 plus y4. This was a ReduceScatter. If you are not able to recall, go back or open the Jack scaling book, look at the example, and you will figure out that this is what we want to finally achieve. So we are going to try that with the reduce operation here. Now we get back here, two devices, the shard sizes are 2, ut, so u was looking something like, so ut now becomes, right, column to row. Right, we are happy with that. Do the canonical product. This would look something like this by this. So it's gonna be a little bit wider, so I'll show it here. 1 0 0 1 1 0 0 1. So the same example on device 0. Device 0, I have y1 y2. Device 1, I have y3 y4. How they're gonna look like? You can think of them as stacked up. So y1 y2 y3 y4. Now we have to multiply these two. We calculated this, and stacking up the device 0 and device 1 partial sums, right, try to do the multiplication. This is 2 cross 4, this is 4 cross 1. This is gonna look like this. 2 rows, single column. Now this is exactly what we needed. Device 0 actually got them summed up and sharded. Device 1 got them summed up and sharded. And that is the reduce operation. I hope from the Jack scaling book, at least when I read this for the first time, I wasn't able to grasp it at all. But from this explanation, I think this should have become clear.
So before starting our parallelism methods, we need to discuss a little bit on LLM math. So I'm on the Jack scaling book. On the section, all the transformer math you need to know. So let me get straight to the point. The first thing we are going to note, if I have to do a dot product matrix multiplication between two matrices A dot B, and the individual parameters are NP and PM size for A and B respectively, then the total number of flops or the total number of computations, so these are either going to be matrix like small multiplications or additions, right? So the total number would be 2 NPM. If you want to find out how that works, this is a good animation. or just write a simple like 3x3 matrix multiplication and you will figure out how the 2 NPM comes. The next thing we are going to talk about is the 6ND rule. In my previous video on GPU architecture and rooflines, I have already discussed how this comes up. But in this rule, we are trying to figure out how many flops do I have to, or how many computations I have to do in my training run. In this example, we are doing a simple case because LLMs are just matrix multiplication. C equals to A dot B. In the Jack Skellington book, they have considered B to be the weight matrix and A are input activations. You can consider them as the tokens and the input embeddings. What happens when I do A dot B? The number of flops, let's say this is the size of A is NP and B is PM. Then we know in the forward pass, we just have to multiply them and the number of flops or computations will be 2 NPM. That is great. Now what's going to happen when I'm on the backward pass? Try to think. I'll have to calculate two things, gradients with respect to A and gradients with respect to B. Right, because this has to go to the previous layer and B are the weights. We have to update the weights with the gradients. So I'll have to calculate, and this is exactly what's written, del L by del B, del L by del A. So I'll have to do twice the computation with comparison to my forward pass. That has been exactly written here. So 2 NPM plus 4 NPM in the backward pass, 6 NPM is the total number of computations I have to do in my training run. Let's say a single step. Now, how does the 6 into number of parameters into number of token word comes up? See, as I said, NP and PM. PM was my B, B was supposedly my weight. So PM is the number of parameters in the matrix and thus N is the number of tokens. Thus I can take that as 6 into number of parameters into number of tokens as the approximation for what? The training flops that I'll have to do. Now we are going to cover some transformer math. So this is not a transformer from scratch video. So I'm going to go very quick here. Why are we doing this? Because in the end, I want to tell you that attention flop are comparatively very less to MLP or feed forward network flops. Let's get into the diagram from the Jack Skellington book. It looks a little bit scary, but it's not the typical GPT-2, GPT-3 architecture. It's from Llama's architecture. Why can I say that? Because the number of query heads and number of key value heads are having different notations. They are not equal. When did we start doing that? With latest Llama models, when we started doing GQ or MQ, multi-query attention. How do we get started? You have multiple sentences, multiple examples, you make a batch of that. So you start with BT. You take that and you move on to with your D model or your embedding dimension of the model. So you have BTD. After that, you move on to the attention layer. It's nothing special. You have your QKV heads, you do your matmulls, you take a mask on your attention. Why do you want to take a mask? Because this is training. You don't want your future tokens and previous token to attend to each other. Then what's going to happen? Finally, you are done with your attention and it's going to project outwards again into BTD. You want to keep your BTD same. Then after the attention, you move on to your MLP or feed forward network. Here they have taken exactly two input weights. You can consider that as a single weight. What you want to do here? You take your BTD, you project it upwards, you do your activation, be it ReLU, GeLU or SWI-GeLU, and you finally bring it back into BTD. This happens for a number of layers. You can specify the number of layers. I guess it would be L. Yes, number of layers. Attention MLP, attention MLP. These are also connected via residual networks. Finally, when all the layers are complete and you are at your end with the BTD, what's going to finally happen? You are again going to project it to the vocabulary size. And finally, why do we project it to the vocabulary size? Think on it a little bit. You want to predict the next token. So I have opened the config JSON for Llama 3.1 405 billion parameter model. The vocabulary size is 128,256. So finally, every token, because I'm going to predict the next token, for every individual token, I have this size of row. What do I get from this? It's normalized, so it sums to 1. These are the probabilities. As my vocabulary size is this much, I have these many, let's say, tokens or words that I know, and I want to predict the next one. So these are probabilities. Pick out from this, sample out from this distribution. It's not always the case that you take the highest probability, but you try to sample out from this distribution and you finally get your answer. And that is how the forward pass works in normal transformer block. I think I went really quickly here, but that is how it's going to be because we are here trying to learn distributed training. Now let us move on to global flop calculation and the parameter calculations. We'll start with MLP or the feed forward network. Comparatively easier to understand. As I said, we have two weight ins, in1 and in2, and this is corresponding to activation or activation functions. It's exponentially small compared to the other operations, so we'll ignore that for now. And this is the outward projection. How do I calculate the number of flops? So calculate the parameters is very easy, like df, d into f, d into f, d into f. How do I calculate the flops? If I just had to multiply these two, this would have been just 2 BTDF. Remember the 6ND rule? 2 for the forward pass, twice of that in the backward pass. So 6 BTDF. For this, and for this, 18 BTDF is the training flops, considering MLPs for each layer. Now we'll consider attention. So I have the QKV heads and corresponding their outward projection. So there are going to be multiple heads, and n and k are not equal here because we are considering a grouped query attention or multi-query attention here. You can just like try to do a multiplication. You have to think of the 6 factor because of the 6ND rule. You have only 4 matrix multiplications in the attention. Of course, the operations are also important. Q dot k transpose, and finally you are doing a dot product with v. You'll get these values. So when I'm discussing attention flops, I'll be summing this and this. Finally, coming to point, we want to take the ratio of your attention flops and the MLP flops. Just try to write those down. Two things we have taken into notice here, that f has been taken into f equals to 4d. Where does that come from? In GPT to GPT-3 architectures, when you are using your feed forward network, you multiply your BTD with your WN matrix, that is DF. So you project your BTD to BTF. F is mostly taken 4 times of the inner model dimension. And they have considered, for simplicity, vanilla attention. So they are not taking different number of query heads and different number of KV heads, and has been taken equals to K. Finally, this fraction comes out to be T by 8D. So the conclusion is, for normal cases, your context length would comparatively be very less to 8 times your inner model dimension. So the attention flops are comparatively really less to the matmults you do in MLP or your feed forward network. So when we are discussing further in the video about parallelism techniques, for flops consideration, we'll only consider MLPs or the feed forward network.
Discussing just a little bit of backprop math, because further in the video we are going to be using it quite a lot. Simple example, C is A dot product B. I'm backpropagating from the loss function, so loss has been calculated. I came to this layer, C is equals to A dot B. A simple example, I'll also derive just a little bit, but remember these as facts. Del L by del A equals to the global gradient del L by del C dot product B transpose, and similarly for B, A transpose dot product del L by del C. If you can remember those derivatives as fact, you can move forward to the next section. I'll give you just a little bit of intuition. How do you calculate derivatives with respect to A and B? What have I done here? Calculated these values for individual values, normal dot product. Now I want to calculate this. This would be similarly a matrix of the same shape as A, right? Only then you will be able to accumulate those gradients. If I am able to find out individual values, I'll get to this answer. How do I calculate, let's say, this? Now, whenever A11 comes, let's say this, what's the local derivative with respect to A11? This term would cancel out or turn to 0. It's a constant, right? And the global derivative. Where else does A11 comes up? Here. Local derivative. Write down all the four terms and you will see that this is actually a dot product between two matrices, and this would turn out to be dot product between del C and B transpose. Similarly, you can calculate for B as well. This was the intuition. I would suggest that you remember this as a fact. We already discussed in detail that attention flops are comparatively really less to MLP or feed-forward network. Thus, as per the Jack scaling book conventions, we'll treat a transformer as layers of MLPs. A very simple MLP, just inward weights W in and outward projections W out. So your inputs BD would scale to BF, then again back to your output would be same as your inputs. In the entire discussion, we'll be considering the data type to be in BF16. So each parameter would be taking 2 bytes of data. So finally, let's get started with the first parallelism technique. So let us get started with data parallelism. Here I'll try to build a little bit of intuition. Why does this exactly work? How it got shaped into? Think about batch size. I'm very happy when I scale my batch size, right? If I keep on increasing my batch size, I'm always in the compute bound regime. My GPUs, my devices are always running at their maximum. I'm very happy when I'm increasing this. But there is gonna be a wall. Like per device basis, per hardware, I can only increase my batch size up to a certain limit. Why? Because all your attention flops or your attention memory, MLP memory, will increase as you scale your batch size. Thus, you can have an upper wall to how much you can increase your batch size. But I'm always happy whenever I can increase my batch size because it will increase the throughput of my training. So is being compute bound the only reason for having a large batch? No, that is not the final answer. Actually, you want your model to see a large part of your data or a large distribution of your data. Why do you want that? Suppose my batch size initially was 100. I'm training a model on, let's say, a coding task. These are 100 Python examples. I calculate the loss, I calculate the gradients, I update my weights. I now change my effective batch size to 5. 5 sentences or 5 code examples are now being passed for my forward pass. I calculate the loss, I calculate gradients, I update my weights. Suppose this had one bad example, like a Hindi sentence or a general English sentence rather than coding examples. These are bad for my model. It would have a really bad loss. These would have like effectively bad gradients and my weights would move to a non-generalizable position, right? I want my model to generalize well. It should be effective in whatever task it's been trained on. Now consider this example. A large distribution of these like effective batch had really good examples. I had one bad example. Just think, this would create a much better loss, much better weights, and a more generalizable model. So researchers found a way to increase your effective batch size given your memory hardware or the max your memory can handle. So I've taken a small example. Suppose I wanted my effective batch to be of 9 and my memory, my current hardware could only handle 3. If I'll move to 4 as my batch size, then what's going to happen? I'll get the or out of memory errors. If I were to consider my batch size to be 1, what have I written here? I do a forward pass with this example, I get the L1 loss. And similarly, I have written for all. If I were to calculate the loss for this entire batch, considering my batch size to be 9, L would have been, right, summing these up and dividing by, because I average out in whatever loss I calculate. But the max I can handle, I don't want to move with a single example. I would be like communication bound here. Suppose I can max handle 3 examples at a time. So my micro batch could be considered this. If I start with this micro batch, I do the forward pass and calculate this as my loss. I calculate gradients, but I do not update my weights as of now. I stop here. I move to my next micro batch. I calculate the Ly loss. I'll tell what these comes out to be, but consider them as Ly, Lx as of now. I accumulate all my gradients. I do not update my weights. I'll consider this loss, or this micro batch, I'll get the loss Lz. I'll again accumulate my weights. After this, I would be able to do my weight updation. Now I know like the max I can handle per my memory is 3. My effective batch which I want to have is 9. So the number of steps or accumulation steps I'm doing is 9 by 3 or 3 steps, 1, 2, 3, right? What is Lx here? Lx would have been L1 plus L2 plus L3 by 3, right? These three losses averaging out would make Lx. Similarly, Ly and Lz. If I want to sum these up, or the sum of x plus y plus z, these turn out to be right by 3. I know the number of accumulation steps, and this loss is actually not completely averaged out. This loss is not L. I'll try to, because this is like 3 times of L. As am I doing 3 steps or 3 accumulation steps, I'll divide this by a factor of that number, or I should write S. Now this effectively would become my L loss. So this same strategy would give me the same loss or the same gradients considering a very large effective batch size. Thus I would have to do a lot more computation because I'm doing forward passes, I'm waiting, then a forward pass, then a forward pass, but that's alright. That gives me a really large effective batch size, and this is the intuition behind data parallelism. Let's get into the details of that now. Now suppose I have 3 accelerators, 3 TPUs, GPUs or 3 devices, and I have the same problem. I want effective batch size to be 9, individual device hardware constrains my batch size to be 3. If I'll move to 4, I'll get these out of memory errors. I get 3 examples on each device. Individually, I got these losses. Now I can still think of this as the accumulation step, gradient accumulation. I know the number of steps. I can effectively divide these losses to be considered this as a total loss with batch size equal to 9. This would have been my total loss here. This is actually data parallelism. Your entire model actually stays the same on each individual device. What are we trying to maximize here is the throughput. Parallelly, these operations are happening, and when I move to my weight updation, I give the final loss to all these devices, and the gradient updates the weights in such a way, because my loss is same afterwards, the exact model remains after each step. So finally, let's say I had 1,000 devices, and after 10,000 training steps, each device would have the same model. Now let's get into the mathematical aspect of data parallelism. As per the Jack scaling book, your data parallelism would look something like this. As I said, you will treat our transformers as layers of MLPs, just W in, W out, and you get your output. The only thing in data parallelism that we are achieving is an effective batch size. Your batch is being sharded across the X mesh axis. Entire sentences, if there were 10 sentences, suppose now 5 and 5 are being sharded on 2 devices. Let's move forward with the forward pass, something very simple. Try to multiply or matmul these two, you'll get something like as my first step. Then I multiply this to get my output. Output is BXD. How do I get that? Right, something very straightforward. Why? There was no communication primitive. These underline my case 1 of sharding fundamentals. I can directly multiply everything and I don't have a problem with that. Now let's talk about the backward pass. I have written the forward pass for my data parallelism here. Let's get started with the backward pass. I'll start from the final output. Del out Vx D. Suppose this was the output for nth layer, then I can use the gradients of n plus 1 layer to find this out very straightforwardly. And of course, if this was the loss, this would have been del L by del L, this would have been 1. Now, I move on to the previous thing. This is how I calculated del out. I'll move with the chain. Now when I calculate, let's say this. I've already discussed about gradient calculation or derivatives of matrix multiplications. This would look like temp transpose matrix multiply or dot product with del out. So this would look like rows, columns exchange when I do a transpose. So this is temp, right? This is not gradients. Now think about this case. Can I directly multiply these two matrices? Yes, I can. This is actually the case 3 from sharded matrix multiplication which we discussed in the previous sections. But I would have partial sums on the same sharded mesh axis. So I will get my gradients of the same shape, but I'll have these unreduced sums on my sharded mesh axis. What I'll do, I'll perform the AllReduce communication primitive. That's going to do a ReduceScatter and an AllGather. It will try to get or accumulate those sums and take those individual shards to every device. Now what is the problem here? There is no problem, but when I'm on a chain, let's say I'm moving on a backward pass, I'll have to only calculate those gradients which are actually required in my previous layers. From all the possible nodes, I want to accumulate those gradients and keep moving back to calculate gradients. Now think about W out, the weights of my model. I do not need these in my previous layers. I only want this because temp has been used in the calculation of my previous layer. Thus, I can do this at some later point of time. I've already taught you this, but suppose I don't do this as of now. I move on to the next step in calculating dtemp. I'll just rub it out a little bit. We understood how we get to dw out. Now think about dtemp. We have already discussed this, how we get out with this specific problem. We get del out matrix multiplication with W out transpose. The shape should maintain, right? BXD transpose is DF. Are we getting this as the same shape as temp? Yes, we are. So we are moving correctly. Write this out. Directly we can multiply, no problem here. So we get dtemp in the shape of BXF. We understood how to calculate dw out and dtemp. This is on the critical path because I need this to calculate dn and dwn. Let's get on with dwn. That would look like in transpose multiplied by temp, dtemp, sorry. This is how it would look like. I can compare the shapes. In transpose d, bx. Yes, we get the shape of dn. But can we multiply these? Again, the same problem. Case 3 sharded matmults. I must get the answer in a reduced form on the sharded mesh axis. Now I'll do the AllReduce. What it's gonna do? ReduceScatter, AllGather. But I have the same concern as I had with DW out. I do not need to calculate this as of now. Why? Because this does not depend on the previous layer. Because let's say this is the nth layer, n minus 1 layers outputs won't be dependent on wn. This is just based on this layer. So I'll focus on calculating din. Finally, we got into calculating derivatives for our inputs. This would be the temp matrix multiplication with wn transpose. This would look like a standard matrix multiplier. Thus, in the backward pass, we had to do two AllReduces for DW out for calculating the weights of the models. Like when I said we can do these calculations at a later point in time, I meant these are not on critical path. As I said, critical path is when I'm calculating this, I actually need this in gradient calculation of my previous layer. So the backprop cannot completely happen until and unless I get the derivatives for this value. But this is not the case for the weights of this specific layer. So these can be done async, or whenever our devices are free or they have more time, they can at a later point of time utilize that time to do these operations. One thing to point out in data parallelism is that we all reduce on the average losses. Thus, when the all reduce happens, we get the weights to be totally same on all individual devices. Why data parallelism? As long as you can scale your number of chips, you can scale your effective batch size. Your throughput would also scale with the same number. This is something like if on a single device, if and only if your model can fit on a single device, and you do data parallelism with like thousands of chips, you do not have an end to the number of chips, you can move your training time from like let's say 10 years to like a single month or even less. The problem is the same. Your model should fit on a single device. That means you won't be able to train really large models like GLM 5.2 or DeepSeek. I have talked about the GPU memory wall in my previous video, but I'll still briefly discuss it. Suppose I have a 10 billion parameter model. Its raw weights in BF16 would be 20 GBs. For my optimizer stats, they would be in full FP32. Let's say I'm talking about Adam. These would have 4 times 2, 8 times 10, so 80 GBs of space would be required by my just the optimizer states. So a bare minimum of 100 GBs is required by this model. So you can think of this as a standard rule. HBM by 10 is the number of parameters you can actually have on a single chip to be trained with. I showed you a section of prerequisites for this roofline analysis. We'll be doing this for every method. We are trying to achieve something which is called being compute bound for data parallelism. We'll get started. First few things we'll assume: every operation and every parameter which we are storing is in BF16. In the backpropagation or in the backward pass, we have two AllReduces. In the forward pass, we did not have any sort of communication. Whatever I'll be discussing here, be it time for the math or the time for communication, this would not be for the entirety of the training run, but just a single time step. And of course, not for all the layers, not for the complete model, but for the single layer which we have been discussing before. For data parallelism, the forward pass didn't have any communications. Thus, it would always be in the compute bound regime. In the backward pass, we had the communication overhead of two AllReduces. So we'll be only thinking about the backward pass for data parallelism. So getting into the rooflines for data parallelism, C is the per chip flops and WICI is the bandwidth between the inter-chip connect. So this is not the HBM bandwidth, but if I'll consider two devices and the physical link between them would be able to transfer bytes per unit of time with this scale. First, we'll discuss about time for communication. As I said, in the forward pass, there are no communications. It is compute bound. We will be discussing this per layer for the backward pass. In the backward pass, we had two AllReduces. What's the time for an AllReduce? It's twice the time of an AllGather. What's the time for an AllGather? The amount of data I am bringing together from the shards divided by WICI. Fine, we'll discuss this. What are the two things we are doing an AllReduce with? The two weights. Right, I can still consider the parameters to be DF or FD only because they are like just rotated. BF16, I would require 2 bytes for each parameter. Fine, this is a single matrix. I have to do this for 2 matrices and an AllReduce. This would be the time for 2 AllGathers, right? This I'll multiply by 2 to get the time for 2 AllReduces. This divided by WICI or 8 DF by WICI would be my time for communication per layer in the backpropagation. Now discussing the time for math or the computations. I majorly had two major matrix multiplications with the first W1 matrix and this temporarily with W out to give me BD again. 1 point, this was actually, if I'll think of the local shape, this would be not all the rows but B by X rows. So I'll have to think in this manner. When I multiply two matrices of sizes NP and PM, the amount of flops that's going to happen would be 2 NPM. We have discussed this previously. If I have to think about the time for math, this would be all the flops which I have done divided by flops per unit of time my GPU can offer with a given D time. We'll think on this. Per multiplier, we had something around 2 BDF NP into PM would give me how many computations? 2 NPM. This was 2 BDF by X because the sizes were really small. I had to do this for 2 matrices. And one more thing. From the 6 ND rule, remember, we are doing the rooflines per layer for the backward pass. This can be considered as the T math for the forward pass, but in the backward pass, I require twice the computation compared to forward pass. This would be my T math. So for the time per layer for the backward pass, this would be max of T math, comma T communication. And due to physical constraints, we can think of this as a lower bound. To be in the compute bound regime, I want one thing. This is what we conclude for data parallelism. B by X should be greater than C by WICI. Now what is this factor? This is not arithmetic intensity, this is operational intensity because this is not the HBM bandwidth but the ICI bandwidth. For TPU V5, this number is approximately 2550. For something like GPU B100, this would be approximately 1000. What can I think of this? B by X. This is the batch per chip. The batch per chip has to be greater than the operational intensity of your hardware. This was the roofline analysis for data parallelism. One more thing which I like to point out, for TPU architectures, we could have 2D and 3D meshes. Your like bidirectional bandwidth can double or triple based on that. As you increase your bandwidth proportionally, your time for communication would also proportionally decrease. Now we'll start with the second parallelism method, that is fully sharded data parallelism, FSDP. This is also called zero sharding. As you can see in the name, data parallelism is here, thus we'll still be sharding by our batches. This would look something like our batches or inputs are still being sharded, and our weights are also being sharded. And finally the output would look like same as the input. Our weights are being sharded here. Now why did we move to FSDP and not data parallelism, pure data parallelism altogether? Why won't we stay there? This is because two reasons. First, we'll keep the entire model on the same device if we were using pure data parallelism. We cannot scale beyond a certain size or parameter limit. And secondly, in the backward pass, when I am doing these all reduces in my pure data parallelism, I am passing all the gradients, like complete weight gradients, to all the devices because my entire model, complete model, is actually on the same device. These two things will try to save memory and compute with FSDP. So let's look into the algorithm now. Starting with the per layer forward pass, inputs multiplied by Wn. Case 2 of matrix multiplication, sharded matrix multiplication, we'll do an AllGather for Wn. Now think about this operation. I'm not doing this for the entirety of the model. This is per layer. I can maintain a buffer of, let's say, 5 layers. If I'm on the 4th layer, I can have my W in and W out all gathered beforehand when I'm doing my forward pass. And for the, let's say, 10th or 11th layer, my weights are still sharded. So I'm maintaining this buffer beforehand so that I can overlap with my computations. So I get this. Next, I want to do again, what can I do here? I would all gather. As I said, I would maintain a buffer of for a few layers, let's say 5 layers. If I am currently on the 6th layer, then for 7th, 8th, 9th, 10th and 11th layer, I would have complete weights on all my devices, and from the 12th layer, I have 80 layers in my transformer. From the 12th layer, my weights would still remain sharded. So I can do this beforehand because this is not on the critical path. I'll not need these weights on my n+1 layer if I'm on my nth layer computation in my forward pass. Finally, I get, if this was the nth layer, then this would become the inputs for the next layer. Otherwise, I can calculate my loss if this was the last layer. This was the forward pass. Let's start with the backward pass. I've written a small example for the forward pass, which we just did. We'll start, this is the final output. We'll correct or calculate. If this would have been the loss, rate of change of loss with respect to loss 1. And I would use, if this was some middle layer, I can use the next layer's inputs or next layer's input gradients to calculate this. Very straightforward. Now I have this, I move on to calculating these two values because this produced this. So I'll move as a chain and do my back propagation. I want to calculate dW out. How is this going to look like? This would be temp transpose matrix multiplication D out. Fair. how does temp look like? BXF. Case 3, sharded matrix multiplication. If I'll do this, I'll have an unreduced product or unreduced partial sums along the sharded mesh axis. So I'll get at this point of time in pure data parallelism, we did AllReduce. Here, we'll not do that. We'll do a ReduceScatter. I'll tell you why. This would look like. How are the original out weights looking like? Now think, if I would have done an AllReduce, I won't have the shard, I would have all the outward weights on all the models. Do I want that? No. Think of this. I have shards of this W out on each device. If I would share the gradients of those specific shards, I can update those weight shards only. I do not want to give the complete gradients, which I was doing in pure data parallelism. Why? Because I actually don't need them. My W out is already sharded on all the devices, so I need only those specific sharded gradients to update my sharded weights. A lot of sharded word here, but you get the point. That's why, or that's what we are doing here. After this, we'll move on to D10. This would look like D out matrix multiply with W out transpose. If on each device I am only having shards, how do I get this? We'll talk about this. D out looks like now this has a dx here. The contracting dimension is sharded. Case 2, sharded matrix multiplication. We'll all gather the W out. Again, in this case, this can be done ahead of time. Why? We can create a buffer. Again, what we were doing in the forward pass, a buffer of let's say 5 layers, because this backward pass is being done per layer basis. For 5 layers beforehand, I can compute this complete W out on all the devices, and I can just do the sliding window. You'll do an AllGather here. I'll rub a little bit and get back. So we calculated dtemp. Moving forward, temp was created from multiplying in and dot product with in and wn. Let's go to dwn. This would be in transpose matrix multiply d10. Fine. In transport would be this would look like case 3. What are we going to do? AllReduce? No, ReduceScatter. The same case what we discussed with W out. When, so this would initially look like unreduced partial sums across the X mesh axis. We do the ReduceScatter and get fine. Now let's calculate dn, the final part. Again, I'm going to need this entirely from that same buffer which I was thinking about maintaining for W out. I'll maintain the complete weights beforehand for W in. D temp now looks like this is DF, so straight up matrix multiplication, we get dn as the shape of bxd. This was the entire per layer backward pass. Moving forward, FSDP gave us two really big advantages. First, I'm not bounded by per chip memory. I can train much larger models, like I can train a DeepSeek or GLM type model with FSDP. Secondly, we do not do any unnecessary work. In pure data parallelism, we are doing all reduces, sharing all the gradients, updating all the optimizer states. Here we are doing that for those specific shards, so saving a lot of memory and compute. Now for FSDP, when I did the forward pass and backward pass, we achieved this. In the forward pass, we had to do two AllGathers, and in the backward pass, 4 communication primitives, namely 2 AllGathers and 2 ReduceScatters. Of course, this part has the more number of communications, so we'll think about this for our per layer roofline analysis. Now, what if I tell you the roofline analysis for the backward pass for FSDP would be exactly same as for pure data parallelism? Think of this: backward pass, same weights, same inputs, but remember we did 2 AllReduces there, right? So these are different, but remember, AllReduce is not a communication primitive because it is ReduceScatter plus an AllGather. So this effectively becomes 2 AllReduces. I'll leave this as an exercise. Try to do the rooflines, calculate the T math, calculate the T communications. For the backward pass, for FSDP, this would require twice the compute compared to forward pass. As per the 6ND rule, you will get the same answer. Our per chip batch size should be greater than the operational intensity for your required hardware, and thus we would be able to stay compute bound. Starting with our third parallelism technique, that is tensor parallelism. How does this differ with something like FSDP? In FSDP, before our matmults, we are trying to gather all those shards of our model weights. Here, the difference would be we'll be sharding across our context, not our batches as of now, but along our context, and we'll try to gather those during our matmults. So inputs and outputs would be all gathered. This is how it's going to look like. So my context is sharded here. And the outputs would resemble inputs. This is per layer tensor parallelism.
And here we are again on tensor parallelism with the jack scaling book on the training section. And why am I here? Should I be explaining the forward and backward pass complete algorithm, deriving everything from scratch on the whiteboard? No, not right now, because I have done that with pure data parallelism and FSDP. So I would love if you would write this down with a pen and paper. If I'll do the same steps, because almost all the steps would be identical. If I'll do the same steps again and again, the video would become too long. So if this gets a little bit harder, then I would suggest that you pause the video, try to write it down, and once again watch the DDDP and FSDP sections. One more thing, tensor parallelism is also called Megatron sharding or 1D model parallelism, and I think I can move directly to the algorithm. As I said, in the forward pass, from the final layer's output, we are trying to calculate our final losses. Okay, so we'll start with the inputs, we'll do our matrix multiplications with the weights, and finally get the outputs. That would be our forward pass. As I said, with the inputs are sharded by context along the Y mesh axis. So here we'll not be all gathering our weights, but we'll be all gathering our inputs. First time, like an communication primitive is being done, which is on a critical path, because our inputs are actually needed for the next step, that is being multiplied with our weights. We'll all gather, this is on the critical path. So we are like having our GPUs idle here. Now, creating the temp, multiplying our inputs with the input weights. Now, this is like case one. There is nothing sharded on the contracting dimension. We can directly multiply this. Next, I move on to calculating temp with W out. case 3 of sharded matrix multiplications, if I'll multiply these two, then I'll get unreduced partial sums along the y mesh axis, and we denote it like this. What can I do here? As I said, I want my inputs and outputs sharded along the context length. I do not want them completely. So finally, I do not want to do an AllReduce, which would require twice the time of a ReduceScatter or an AllGather. We save a little bit of time here, but this again is on critical path. We will either require this for calculating loss if this is the last layer, or this would serve as the input for the next layer. Now let us move on to the backward pass. What are we trying to do here? Updating our model weights. Thus we need these two. So let's get started with that. We can easily calculate D out. I have talked about this like twice or thrice in DDP and FSDP. Not gonna say it again. Now outputs, we wanna all gather them, D outs. Okay, so this is on like your critical path. Why do I need D out completely? Look in the forward pass. I got D out. Now I want to calculate D temp and DW out. If I want to start calculating DW out, then this would be temp transpose into D out, this completely. Okay. Thus we want to all gather here. As I said, DW out would be temp transpose and multiplied by this. This would look like FYB into BD. A direct multiplication, no problem here. And now we can like move to calculating. We calculated DW out. We'll calculate D temp now. D temp would look like D out into W out transpose. D temp would look like D out completely into W out transpose. So this would be BD into D into Fy. Again, a normal matrix multiplication, no problem here. And we can discard what? D out BD here. Okay. Again, now next point is we have calculated D temp. Now we want to calculate D in and W like DW in. For calculating DW in, this would actually look like N transpose into D temp. Very cool. So I would need the complete D in, right? That's what we are going to do here. We're going to all gather our context sharded inputs, and like what is being written here, that this can be skipped by sharing one from the forward pass. What does that mean? I can skip doing this all gather because I have all gathered in my forward pass. I can still maintain this in my buffer memory, and I do not want to perform this communication primitive here. We can save this cost. Now, how does DWN look like? This transpose into D10. So DBBFI direct multiply, we do not have a problem with this. Finally, we are at the end step. We want to calculate D in. How is that going to look like? D temp into W in transpose. So how is that going to look like? D temp, BFI, DFI. So we'll transpose this. So this would look like BFI, FYD. Third case, sharding matrix multiplications. We'll get partial sums along this Y mesh axis. We calculate DN. Again, we talked about this. Do I want to have complete DN in like, do I need this sharded? So should I perform a ReduceScatter or an AllReduce? At all points of time when I'm performing tensor parallelism, I actually only want my sharded context on all the devices, not the complete batch. Thus, I can only perform ReduceScatter, and this unreduced sum is changed into shards, and we complete our forward and backward pass. If you feel this was a little bit faster, I would like recommend you to stop the video or rewatch the video. Start with DDP or FSDP parts where I actually did this on a whiteboard. Open your pen and copy and try to write this down. This would become a piece of cake for you.
When we did the forward and backward pass for tensor parallelism, we observed two things. In the forward pass, we did one AllGather and one ReduceScatter, correspondingly for the inputs and outputs. And from the backward pass, we did two AllGathers for inputs and outputs, and also one ReduceScatter for the input. Definitely looking at this, we feel that the backward pass has more communication, so we should roofline along the backward pass, but these both are actually the same. If you look, we did an AllGather for the inputs and one AllGather for the input as well. We can maintain a buffer, as I explained in the video. We can maintain a buffer where we can just save that AllGather for the input and utilize it here and just convert that AllGather from 2 to 1. both become entirely same considering the communication overhead. So I'll do the rooflining across the forward pass now. Considering the time for math, forward pass for tensor parallelism, we majorly did two matrix multiplications, BD into DF and BF into FD. And the local shapes, of course, we were having a sharded dimension. So the number of flops would be 2 BDF by Y. And this is for a single matrix multiplication. We have two of them, considering both the weights. So the time for math would be this divided by the peak flops per second my hardware can offer in BF16. So this would be my time for math. Now considering the time for communication, we did an AllGather for our inputs and a ReduceScatter finally for the outputs. So the time would approximately be same. We'll have the total number of bytes being all gathered. That would be, the parameters would be BD, but we are using BF16. So this would be 2 BD, each parameter requiring 2 bytes. And I have two such operations. This would be for AllGather. Twice of that, this would be considering both AllGather and the ReduceScatter. Divided by byte second move per unit of time, that would be T comps. The overall time for our per layer forward pass considering tensor parallelism would be at least the max of what we calculated, T math and T comps. And to be compute bound, our T math must be greater than T comps. Let's put in the values and find out what comes out. So this becomes F greater than Y into C by WICI is our operational intensity. So I'll still write it down. This is what we can conclude from here. We are trying to figure out with what mesh size can we confidently do tensor parallelism being compute bound. We got till this situation. Now C by WICI is constant. It's a hardware constraint, my operational intensity. I'll call it K. So my Y needs to be less than F by K. With a fixed hardware, K is constant. My inner model dimension F would also be constant. Calculating this in most reasonable cases, Y is in a range from 8 to 16. Here we are confidently compute bound with tensor parallelism. Coming to the fourth method, that is the combination of fully sharded data parallel and tensor parallelism. Why are we even doing this? Because to get best of the both worlds, let me write it down. Sharding our batches as well as our context and of course our outputs would look like the inputs. This in a nutshell is the combination of FSDP and TP. Let us try to build some intuition here. As we have discussed, when we were considering tensor parallelism, we were all gathering or reducing across the inputs and outputs. With FSDP, what we did was all gathering and reducing across the weights. So suppose this input in the start when I am trying to do pure tensor parallelism, now think my extent of FSDP, the more mesh axis X I have, the more devices I have along the X mesh axis, this communication cost would reduce because the local thing which I am all gathering is actually less in size now. If I would consider for FSDP, if I want to all gather across any weight, so I would do that along the X mesh axis. For WN, this would look like, and this would look like D comma Fy, right? Now think on this. If I were to increase the size of my Y mesh axis or the scale of my tensor parallelism, this communication primitives cost would reduce by a lot because my Y as the local shapes would become thus getting the best of both the worlds when we combine FSDP and TP. We'll try to reduce our per chip batch size even more than pure FSDP now.
And we are back on the Jack scaling book discussing combined FSDP and tensor parallelism. I'll just skim over the complete algorithm because we have done this from scratch, like written it out when we were discussing DDP or FSDP. We went over through it completely when we were discussing pure tensor parallelism. So I'll not do that again. The steps are very, very straightforward. I would love if you would open your notebook, pick up a pen and try to do this yourself. Two things to note: whenever we'll be doing steps corresponding to tensor parallelism, we'll have to think on all gathering the inputs and outputs. This is going to look like this, and this would be on the critical path. And as we have discussed with pure FSDP, what we do, we all gather the weights, but we can maintain a buffer. Like if we are on the fourth layer, we can actually get or all gather the weights for the fifth, sixth, seventh, eighth, ninth layer. So this can be done ahead of time. You'll have to remember that. If you'll just skim over the forward pass and backward pass, it looks that there are more communication primitives involved in backward pass. So we might want to do the roofline analysis considering the backprop. But remember, when we do rooflines, we think of communication per flops. And in the backward pass, we have twice of that, twice number of flops compared to the forward pass. So if you'll calculate, you'll find that communication per flop would be higher with the forward pass. So we'll do the rooflining for the forward pass here.
Now we move on to rooflining. We'll consider, as we are talking about combined FSDP and TP, forward pass per layer. Let us discuss about comms first. So we'll have to think individually for the comms of FSDP and tensor parallelism. Here we were considering for inputs and outputs, and this would be considered for the weights of the model. I'll start with FSDP. We'll all gather along the X mesh axis the weights which are of size DF and FD, and we are considering BF16. Parameters we can say DF, and the actual in bytes this would be 2DF. We'll have to do this twice for W in and W out. And are the local shapes, the final local shapes after being all gathered? This no. This they would be, so we'll divide by Y, and this would be my time for FSDP, as I'll divide by the bytes I can move per unit of time. One more important thing, when I'm considering TPUs, I can have the Z mesh axis as well. If I were to provide that to FSDP, so when I'm all gathering my weights, let's say along the X mesh axis, and I've allowed the data movement from the in and out of this plane of the board, then the amount of data I can move, my effective bandwidth would become twice, because Z is also being allowed. So the number of mesh axes which I'm allowing to FSDP, I've written that or denoted that with mx. Now the time for tensor parallelism. I'm doing this for the inputs and outputs. Parametric size would be BD. In BF16, each parameter requires 2 bytes of data. And I'm doing one AllGather for the inputs, one ReduceScatter for the output. Effective time would be twice. This is the amount of data am I moving? No. Actually, this would be still sharded among the batches. So I'll have that X factor dividing by the amount of bytes I can move through the physical links, WICI. This would give me the time, and as I have called about the physical mesh axis which I have allocated to FSDP to be mx, similarly I can think that to be my for TP. If I am all gathering or reduce scattering along the Y mesh axis, and I'm gonna allow tensor parallelism's communication primitives to use the Z axis as well, Z mesh axis, then the effective time would reduce by a factor of my, the physical mesh axes which I have allocated to tensor parallelism. So remember these terms. Now talking about the time for computation per layer forward pass for combined case of FSDP and TP. We are doing two multiplications with, like, if we'll think a BD into DF and BF into FD. One thing we'll notice that 2 BDF would be the minimum number of flops per multiplication for W in and W out, considering this. Now, you look in the algorithm that whenever we are multiplying, both the axes are being sharded. So we'll have a division case because the local shapes would mostly look like B by X or F by Y. We'll have this factor in, and the flops my hardware can offer per second. This would be the time for T-math. The communications are independent. Either we consider FSDP or TP. So the time for communications would be at least, because there are hardware constraints, max of FSDP or time for TP, right? So we'll have to figure out the minimum possible from both of these to have the minimum possible TCOMs. Now bring out the common stuff. A few things will change here. That is, the number of chips would be n, and the number of mesh axes is 3, right? You can only build a 3D torus, nothing high dimensional is possible yet. So, like, one thing you'll remember is this, and the total number of devices would be n. Now we'll try to write this in terms of only x. Now writing y in terms of x. Now think of this, we want to minimize this number. I want to bring down my time for communications to the lowest possible. F is constant, n number of devices, mx is constant, b and my are also constant. So this looks like kx comma, like, let's say z by x. If I were to draw this function, let's say this one is fx, this one is gx. This one increases with time and it's like monotonically increasing, it will never go down if I'll just keep on increasing the value of x. And this one would keep reducing all the time. This would be decreasing monotonically. When would be the time when I can find the minimum of these functions? That would be when fx would be equal to gx. Now equating the two, I would get x to be but what does x signify here? The first thing, this would give me the minimum communication time, so this is definitely an optimal value. But what does this signify exactly? At the start of the section, when we were discussing the intuition behind combining FSDP and TP, we said that we want to get best of both the worlds. When we were initially doing those AllGathers, those communication parameters, we were discussing that when we increase our FSDP, the AllGathers time for TP would reduce and vice versa. That means this optimal value would amount us, given that a batch size is known and you already know these values n and f, you know the like ample amount or the perfect amount of FSDP that would make the overall training run in the compute bound regime. A short example given in the Jack scaling book, with a batch size of 48K, you have 64 devices in a cube 4x4x4. Inner model dimension is 32,768. Suppose you want to give two mesh access, physical mesh access to FSDP. So I'll take mx to be 2, and this would definitely become 1 because these needs to sum to 3. X would be this would approximately come out to be 13.9. So how do I want to divide my number of devices along the X and Y mesh axis? I can give something greater than this. So X can be 16 and Y can be 4. So these multiplied would sum to N, which will be 64. This is how you can divide between your FSDP and TP here. We found out the optimal value of X or the amount of FSDP when we were trying to combine FSDP and TP. And if you got your X optimal, and you know X into Y is the number of total devices, you also get your Y optimal or the value of tensor parallelism that you can particularly afford to have your minimum communications. Still, we have one more condition left. We want to find the condition for being in the compute bound region. That would be T math greater than the time for your communication. I'll write down the values and simplify this expression. We have already discussed that at X optimal, if I would put X optimal here, this would become N by X optimal. So I can also replace Y. These two values would become equal. So I would be able to simplify this expression more, like use any of these two expressions now. Let's do that. So I have chosen this term. Try to put the optimal value of X, which we calculated. Right, and try to find the final condition. I have now simplified the expression. K here is the operational intensity, C by W ICI, and mx into my should be 2 because these sum to 3. We could only have a 3D structure when we are discussing about TPU architectures. Now, your per chip batch size needs to be greater than K square by 2F. Try to add some values here, and you will find out this is like almost 6 to 8 times smaller than when you were only considering pure FSDP. So a combination of FSDP and TP can get you even a reduced number on your per batch size or per chip batch size. There is a small section in the Jack scaling book called Scaling Beyond Pods. So what is a pod? There is an example for TPU V5P. This is a super pod which consists of 8,960 chips. That is a very large number. And what is this? These are the number of hosts which a super pod would consist of. What is a host? It's basically a CPU, like someone would be giving instructions to these accelerators or these TPU devices. As per this architecture, a single CPU or host is connected to 4 TPUs. If I want to scale beyond a super pod, this already is a lot of chips, lot of cost. But if I want to move to different data centers and TPUs talking to each other, what's going to happen? Every host has this NIC or network interface card. These are like the physical things or devices through which two devices would communicate or two computers would communicate, like an Ethernet port. The physical chips inside a super pod are connected via ICI links, which are actually really fast. But when TPUs are communicating across data centers, what's going to happen? We'll have this bandwidth for a DCN, and this would be comparatively very less. Per host, I have 4 TPUs, and a host would be talking to a host of another DCN. So that bandwidth would also be like 1/4, because if a single TPU or all these 4 TPUs want to talk to another system here, then the host is talking to another host. So the overall bandwidth would also become 1/4, the WDCN bandwidth. So we just discussed the basic idea around superpods and data centers. When I'm on a single superpod and I want to scale beyond that over multiple, like across data centers, what I'm trying to do, when I'm in the ICI bandwidth range or when I'm inside a single superpod, I would try to do something like FSDP or Tensor Parallelism, and across the data centers, across those superpods, I want to do something like distributed data parallel. Now let's understand the rooflining for this. Suppose at the moment I have m number of chips. This could be the entire superpod, or some slice, subsection of the superpod. So I would have fewer than 8960 chips. And I want to scale to n number of chips. This could be across the data center to like 10 superpods, 20 superpods, right? I want to scale to this number. Let's talk about what T-math would look like. We know, like, both two multiplications, BD into DF and DF into FD. Two BDF computations. You multiply that with, as I have two multiplications. Suppose I'm thinking on the backward pass, so twice the computation of the forward pass. Now think on the denominator. C is the flops per second a single device would give to me. But all these flops are actually parallelly happening. All the devices are running. So I'll multiply that with n. Think on this for a moment. The time to compute something actually per layer would actually reduce as you increase the number of chips. So the flops per second would raise by the factor of the number of chips you are increasing. Across pods, we were discussing about distributed data parallel, right? And of course, in T-math also we were considering the backward pass per layer. Why? Because in DDP, only the backward pass has the communication overhead, which is to AllReduces. You want to average out those AllReduces for the weights. Suppose we are on BF16, 2DF, and this would be considering two AllReduces, or let's say two AllGathers. The time for an AllReduce is twice the time for an AllGather, and this is happening across the data centers. So W DCN, your bandwidth for data center networking. One more point, this is not complete yet. Across this superpod, when we are doing this reductions, this is happening for this specific slice, those reductions. So your DCN would be scaled by the M factor. This is your T comms. Finally, the compute bound condition, T math should be greater than T communication. If we just simplify this, this would be the final condition when we are scaling beyond pods. Now what does this condition signify? I can write this down to be this is the number of pods. Try to think, we want to scale to n number of devices. I currently have m. This could have been a single super pod. This could be multiple ones. This is the number of pods which I have. So to be in the compute bound regime, my per batch or per pod batch size should be greater than this value. If you went through the training section of the Jack scaling book, you will realize that they haven't covered pipeline parallelism like in depth. There are a few reasons for it. First of all, TPUs have this architecture scheme. They are really good in training when they are in meshes because two TPUs are connected through really fast ICI links. That is not the same case with other type of accelerators like GPUs. GPUs are not really well connected. So a really good training mechanism considering GPUs is pipeline parallelism. Let us first discuss the intuition of pipeline parallelism. Suppose your entire model has 80 layers and I have 4 GPUs, 4 devices. If I were to divide my entire model into equal parts, each GPU or each device would get 20 layers. 80 by 4, 20 layers on each. What's going to happen? I'm going to feed in the inputs. This would give me some partial outputs which I'll feed to the next device, to the next device, to the next device. Finally, this device would calculate the loss, and with respect to the loss, it will calculate its gradients, and the input gradients would be passed to the previous device, and this would be the pipelining or naive pipeline parallelism. I'll use this shorthand for pipeline parallelism. I'll call it PP for now. This is the basic intuition. You will just break your model into slices and put it on different devices and use it as a straight pipeline. The good thing about PP algorithms is that we are always low on communications, and considering the flops, we are almost always on the compute bound region. I'll discuss that in detail, but for example, suppose I have two devices. This had 20 layers, this also had 20 layers. I do a lot of computations, I got the inputs and I do that for 20 layers, but what do I pass to the next device? Think of that. Only the outputs, that's like a single tensor. Meanwhile, my computations are really large. What I'm passing is not heavy as, let's say, AllReduce or AllGather operations, which we were previously discussing. So the communications are comparatively really less, and the computations are really high. As I said, we are almost always compute bound whenever we are discussing PP algorithms. But the problem is the same example which I gave you. This one computes, pass in the outputs, and the same steps continue. I compute the loss, calculate my gradients, move the gradients on the previous device, and in this way, a single step of, let's say, naive pipeline parallelism algorithm completes. When this one is computing, this is idle, and this is idle. And that is true for any other part. When this one is calculating the loss, 3 more GPUs are sitting idle as far as a very naive implementation is considered. So there is another roofline which we'll have to analyze, would be the idle time or idle GPU time. I'll be quickly discussing the operational intensity for this PP setting. Operational intensity is flops per byte loaded. So there's going to be forward passes and later backward passes happening. This is a training setting. Suppose the entire model has n number of parameters, and I know from the 6ND rule, number of flops that gonna be happening in this training run would be 6 into n into d, the number of parameters of the model into number of training tokens. 2ND would be happening during the forward pass, 4ND would be happening twice of the forward pass in the backward pass. If I want to know how many flops, that would be 6 into per stage, per batch. Now, suppose I have p devices, each device would be carrying n by p parameters, right? As I said in the initial example, 80 layers, and I had 4 devices, 80 by 4, 20 layers to each. And I can write, let's say, the tokens to be t. How many bytes move? As I said, the outer outputs and the inputs from here would only move, and with our MLP analysis, right, these were the inputs and these only were the outputs, so this amount of data would be moving. If we consider BF16, to TD I can write, and one time for the forward pass, one time for the backward pass. This would be my operational intensity. Now the intensity comes out to be, try to put in some real values, let's say for Llama models or DeepSeek models, you will find out that the flops which are happening per byte, this number is actually really large, around the factor of 80 to 160. That suggests that in pipeline parallelism algorithms, we are almost always on the compute bound regime. So this is something which we will not discuss moving further whenever I am talking about these various algorithms. Now starting with the naive PP algorithm, suppose I have 4 devices or 4 pipeline stages. Device 0 starts with the forward pass. It gives its outputs to the first device. Now at this point, this is the independent time axis. So at this timestamp, device 0 is doing nothing, device D2 and D3 are also doing nothing, but this first device is computing its forward pass. I'm considering this as a complete single batch. Next timestamp, this passes the inputs to D2, and finally, at this timestamp, D2 passes its outputs to D3. As soon as I get the final stage, I'll calculate the loss and start with my backward pass. As you can see, the forward pass looks like really small, and the width of backward pass is like twice of forward pass. That is also due to the 6ND rule. The backward pass would require twice the time or twice the flops as compared to the forward pass. This calculates its own gradients with respect to the weights. Then for D2, D1, and finally D0. And our final single step training completes. I guess you will be able to observe that most of the time my GPUs are sitting idle. Suppose this timestamp D2, D1 and D0 are doing nothing. We'll try to roofline against this idle time or idle fraction throughout this entire pipeline parallelism section. Let's say I want to think about the idle time for D3 device. So 1, 2, 3, three times it takes to do a forward pass, and 1, 2, 3 into the time it takes to perform a backward pass. This is the time D3 was sitting idle, and how much time was it actually doing some good flops or doing some work? 1F plus 1B. Right. Now the idle fraction becomes and I did this for D3. For any device you will find out the idle fraction would be this value. Suppose P are the number of stages or number of devices. This is actually P minus 1 into F plus P minus 1 into B. And intuitively, if you will just think about the forward pass, this is like a 4x4 grid. How much time am I sitting idle? If you will count, this would be 12. And the time I am doing actual computation would be 4. This is also coming out to be 3. So my utilization is actually, idle fraction is P minus 1 times F plus B. Now I'm not talking about the idle fraction. This is about utilization. So how much time did I actually do meaningful work? 1 into F plus B divided by the idle time. My utilization is 1 upon P minus 1. In this entire section, we'll try to improve on this.
After naive PP, we'll move to GPipe. This is an open source pipeline parallelism training method by Google AI. The idea is very straightforward. The above diagram is of what we have discussed earlier, naive pipeline parallelism. A single batch, you move it through the devices, compute the loss, do the backward pass, and when all the gradients are available, you update your weights, you synchronize and start your next training step. We were very fine with that. The new thing about GPipe is that we'll break down our entire batch into small micro batches. So what would be the difference here? So like I have broken this F0, this entire batch into 4 micro batches. We'll let's say call this into M micro batches to generalize. And the number of devices here are 4, but we'll think of it as P stages or P devices. As soon as I'm done with this micro batch, of course, it's going to take very less time compared to the complete batch. As soon as I'm done with this, I can transfer it to the next device. These outputs would be treated as inputs to the next device, and I can continue with this forward pass for this specific micro batch. And when I'm done with this, I can transfer it to the next device, and within that amount of time, device 1 would also be finished and it would pass that to device 2, and this process would go on considering the forward pass as well as the backward pass. As you can visualize, you can see that bubble has like comparatively become small. If you were to try to calculate that utilization now, that would be 1, 2, 3. Let's say if I'm discussing about the final device, device 3, 1, 2, 3 forward passes, this would be idle. And for 1, 2, 3 backward passes, the time equivalent to a backward pass, so 1, 2, 3, 3b times device 3 was sitting idle. The idle time was 3 into f plus b. Where does this 3 come from? That's from the number of stages. So the idle time would be p minus 1 into f plus b. And what's the time where my device is actually doing some good work, good amount of flops? That is 1, 2, 3, 4. 4 timestamps doing forward passes and 1, 2, 3, 4. 4 timestamps doing backward passes. Where does this 4 come from? As I have broken down this entire batch into 4 micro batches, this comes from M, the number of micro batches. So the time I'm actually utilizing my device 3 is M into F plus B. So the utilization fraction would be the total time where I'm doing actual fruitful work, M into F plus B divided by P minus 1 into F plus B. The F plus B factor cancels out and my utilization becomes M divided by P minus 1. This actually is quite better than my naive case, which was just 1 by P.
With GPipe, I was able to get my bubble fraction or idle fraction to be around P minus 1 by M, P number of stages, and M the number of micro batches I'm using. As I can see, if I keep on increasing my M, I would eventually make this number smaller and smaller and reaching near 0. So I would move to 0 bubble, problem solved. But that won't be the case because I cannot arbitrarily increase and keep on increasing the number of micro batches, because I'll have to maintain those activations on each device, right? And as I increase the micro batch size, the amount of memory would keep on increasing and increasing, and I have a strict limit on individual devices. So there's only a certain hard limit to which I can increase my micro batch size. And we'll try to improve on this specific algorithm with F1B1.
Now we move to 1F1B algorithm under the project Megatron LM. This was created by NVIDIA. How is this better from GPipe? We'll discuss, but let us discuss about the core of this algorithm first. There are 3 major steps. First is the warm-up, next is the steady state, and third is the cool down. Warm-up are also called the fill state, and the cooling down is considered as the drainage state. Why the fill in this word? Because you are adding or you are completely filling your devices, and in the drainage stage your devices would start to become idle with time. In the steady state, this is a good state. Why? Because your models are not idle. Forward, back, forward, backward, forward, backward. The yellow is for backward, and double the width because twice the computation as compared to a forward pass. See, the core aim of 1F1B algorithm is to restrict the activation memory, right? We are not trying to improve the utilization here. Before discussing that, first let us look how do we actually process or like go through this algorithm, because as you can see, we are not moving to the 5th micro batch on device 1. We are doing that much later. As soon as my last device is filled up, I am moving on with the backward pass. So how do we get started? The warm-up steps for each device is equal to P minus R. P is the number of pipeline stages, number of devices, and the rank of that specific device. You can start with a 0 index, or let's say suppose 1 index as well. So P minus R for this would be, P is always 4 in this case, and R would be, let's say 1. So 4 minus 1 would be 3. So I have 3 warm-ups for device 1, 1, 2, 3. And for device 0, I can consider that 4 minus 4 would be 0. So there are no warm-ups. And how do I calculate the steady states for an individual device? Let's say device 4. These would be number of micro batches minus the number of warm-ups. As I have 0 warm-ups and the micro batches for that, this training step is 8. I would have around 8 steady states. 1, 2, 3, 4, 5, 6, 7, and 8. So a single stage is considered to be the forward and a backward. So 8 stages continued would be for device 4, and thus I can calculate the steady states for each device. And finally, the number of drainage steps would be equal to the warm-up steps. Now, before talking about the activation memory, let's do the most important thing, trying to calculate the utilization. And as we have discussed till now, if we'll calculate this for any device, all devices would have that same utilization or idle bubble time. Suppose I start with device 4, I can see 3 forwards which come from the number of devices p minus 1 forwards time, and in the cooldown period 3 backward times, so p minus 1 into b. So the total time I'm setting idle is p plus 1 into f plus b, right? And how much time am I actually doing some fruitful work? I can see 8 number of forward passes and 8 backward passes. The 8 is coming from this training steps micro batches, that is m. So I get m into f plus b, and I can see the utilization is actually m by p plus 1, which is exactly the same as GPipe. What you can do, actually try to visualize a little bit. Move this entire backward passes to the right side and all the forward passes to the left side. This would take the shape of the V which we were initially discussing with GPipe. So we have just rearranged the order, we are doing nothing new, and the utilization or idle bubble is exactly same than GPipe. But what's a good part here? As soon as my last device receives its forward pass, I move on to the backward pass. So I'm trying to reduce my activation memory here. For the last device, I can see I almost have no activation memory, because as soon as I do my forward pass, I continue with my backward pass. For device 3, it's actually on the order of 2 like micro batches. As soon as I have 2 forward passes done, I start with my backward pass, I gain another. So it's like a sliding window of activation memory, and the maximum which I actually carry with myself would be for the first device, which is the order of 4. Where does this 4 come from? P minus 1. So with 1F, 1B, I have moved my activation memory, which scaled to M when we were discussing GPipe, to P minus 1. And this is the best thing about 1F, 1B algorithm.
1F 1B algorithm helped us reduce the overall peak memory activations. But there is still room for improvement in utilization. Thus, next we move on to the zero bubble pipeline parallelism algorithm, also called Z1P. This was originally given by CAI Labs. They have also helped out in the creation of DualPipeV by DeepSeek. So the intuition behind zero bubble PP is that we know that the backward pass requires twice the time for computation compared to a forward pass. And why is that? We are calculating gradients with respect to the inputs as well as with respect to the weights of the model. Now the good part is, we have talked about quite a few times that this is not on the critical path. That means even at a later point of time, I can find the gradients of my weights, given that I have that graph, and just find out this, because this is on the critical path. This would be required by the previous layer. If I just calculate this for now, move to my previous layer and continue with the back propagation or backward pass, and when I'm free, when my GPU is idle and I continue with this, I would be able to better utilize my GPUs. And that is the crux of the zero bubble PP.
Now let us discuss the Z1P algorithm. I am on the original paper for zero bubble pipeline parallelism. This above diagram is considering 1F, 1B, which we have just discussed. As you can see, the backward pass taking twice as long as the forward pass. And this below image is actually for Z1P algorithm. As you can see, the backward passes are taking equal time compared to a forward pass. Now this color is for a forward pass. This light blue color is corresponding to gradient calculation with respect to the inputs, and the green color is for gradient calculation with respect to the weights. So each step is taking around the same time because it is taking the same number of compute. And after the optimizer step, we move on to the next training step. So that is not required. We'll just analyze a single step. What are we trying to optimize here? We are trying to reduce these bubbles, these idle times. After the steady state device 3 is actually never doing anything, we'll try to improve on that part. So how is this any different? It's like almost acting very similar to 1F, 1B, same number of warm-ups, and then you start with the same sense of the steady state and drainage. After F4 or forward pass for a fourth micro batch, almost everything is same. As soon as device 4 gets the F1, it's going to do its backward pass, but only with respect to the inputs, because here we were doing it for both inputs and with respect to weights. As soon as you are done with that, you pass it to the third device and you continue with your second batch, which you had received from the device 3. You do that. This is like the steady state 2, 2, 3, 3, 4, 4. Now, when I get this idle time, why do I get this idle time here? If you'll compare it to here, because here we are doing gradient calculation for both inputs and weights. So it's taking double the time. When I get this free time with respect to device 4, I can do that the gradient calculation with respect to the weights corresponding to batch 1. Just if I have the graph, I can do this at a later point of time. And this is going to continue and continue and continue. At 8, after I am done here, device 3 is sitting idle. But if you'll consider device 4, as soon as I'm completed my like backward passes with respect to the inputs, I'm off the critical path. I can use that time to calculate gradients when I have not done that. So I had actually previously not calculated gradients with respect to the weights for batch 5, 6, 7, 8. I can do that now. You can like, this is like a D queue. You can maintain a queue where you maintain for each device what devices or what batches I have not performed the backward pass or gradient calculation with respect to the weights, and as soon as you are free you can continue doing that, and this way I'm able to improve on my utilization. Let's calculate that now. Now let us discuss the bubble fraction. Why is that different from 1F 1B and when I'm discussing about Z1B? First, for this entire single training step, try to count the idle timestamps for both 1F 1B and Z1B. If you'll count from here, this would be around 36 idle timestamps, and here you'll find out for all the devices for this complete training step, this would be around 12. So 36 by 12 would be 3. So there is at least a 3 times reduction in this entire bubble when I'm doing Z1B. Why is that? Okay, now try to look here. As soon as I'm done with my 4 forward passes for device 0, I'll have to wait for next 6 timestamps. Why is that? Because until and unless I get my back gradients from device 4, then to device 3, then to device 2, and finally to device 1, I won't be able to do my back propagation. That means if I would have done this just for the inputs, this would have taken me half the time, right? So if I would have done this for only the input gradients, I would have required wait for 3 ideal timestamps, but here I did that for 6. First point, that's where I save the time. And secondly, where do I save time again? This is like a consumer producer problem. If I'm not done with my back propagation for batch 6, I cannot give it to device 1, right? So I have this wait times here. Next, I reduce that. Why? Because whenever my GPU is idle, I can move on to the work on non-critical path, which is calculating the gradients for my weights. Now, as I can see, the bubble fraction would have become from P minus 1 by M into now for Z1P, that would be P minus 1 by 3M, because I have reduced my bubble by 3 times. That is the first thing. Now, thinking about the absolute bubble size. For the last device, this should, for 1F 1B, this should have been P minus 1 into B, P minus 1 into F and P minus 1 into B. 3 backward timestamps, right? But here I broke that down into only 3F. The absolute time now has been changed to P minus 1 into B plus F minus 2W. Here, when I talk about B, I mean the entire time for calculation of gradients with respect to input and weights. And when I only talk about W, that means only the time for calculating gradients with respect to weights. So here, the absolute bubble for individual devices would be P minus 1 into F plus B minus 2W.
Now let us move on to DualPipe by DeepSeek. What's the core intuition? What did we achieve with Z1P? There were a lot of cases where we improved, like separating the gradient calculation for inputs and the weights. We were able to save a lot on the bubble fraction, but what DualPipe is now trying to do, suppose I have 4 devices. All the algorithms which we have discussed till now would move in one direction, calculate the loss, and move backwards. So the flow is always in one direction. That is what the dual in DualPipe comes in. We try to break this problem. In DualPipe, core normal DualPipe, we'll maintain 2 copies of the same model. Suppose I have 80 layers in the entire model, 4 devices, so 20 layers each. And then maintain a separate model starting from this side. So if the inputs were going from this side, now in the second model the inputs would go from this side. Now when timestamp 0 starts, I'll have 1 micro batch of data going in this direction and 1 micro batch of data going in this direction. So at every timestamp, I am doing 2 computations. Just after DualPipe was launched, CAI Labs talked about a DualPipe version without the dual in it, or maintaining the model twice. What they suggested, I am giving you a rough overview, then we'll move on to the screen and discuss about the algorithm. You can keep the model in a V structure. And move in this way. And almost achieve the same results as core DualPipe. Now, how is this similar from DualPipe? You can think like when a certain micro batch is doing its forward pass here, some might be doing its backward pass, because these are 2 separate models, and something similar could also be thought about this. When I am doing my forward passes, this layer could also be performing its backward pass. Very similar to how DualPipe functions.
And here I am on the DeepSeek AI DualPipe official repository, and we're going to look into the schedules of both DualPipe and the DualPipe without the dual, DualPipeV, which was actually talked about or discussed in this blog post by CAI Labs. Let's get into it. Now, how is this any different from Z1P? First thing you're going to notice, there is not a straightforward staircase. I can see these orange blocks. In this specific case, they are going ahead with 8 devices indexed from 0 and also 20 micro batches indexed from 0. When there is this empty orange block, this means this is corresponding to the other end, because we are keeping the entire model like twice on the same GPUs. So like from the the inputs are being fed from this side on the model 1, let's say model 1 and model 2, which are on the same devices. Model 1 is being fed with 0 to 9 micro batches, and this is the number 10. 10 to 19 would be fed from the other side or to model 2. As I can see, there is no clean staircase here, right? If this would have been Z1P, this device would first run after device 6 receives its micro batch zeros forward from all the previous devices. Not the same case, because 10 is running and going straight up. Now this would have been the 11th micro batch. This is something which is very different, which we haven't seen in the previous algorithms. How does this help me in improving my utilization or bubble fraction? Think about this. When I was talking about the bubble fraction in earlier algorithms, let's say 1F, 1B or Z1P, I was trying to figure out the number of forwards equivalent timestamps which I was setting idle and the number of backward timestamps which I was setting idle. They were coming around to be a factor of p minus 1, number of stages, number of devices, into f plus b, all in 1f 1b. In Z1p I was able to reduce that a little bit, but the multiplication factor was p minus 1. p minus 1 into z plus b minus 2w. Why was the 2w factor coming? Because I was changing my complete backward to backward for inputs, which was on the critical path that would go straight up, and backward for weights, which I can do at like later point of time or when my GPU is sitting idle. Now, as you can see, that factor of p minus 1 was coming because I had this staircase. It was coming from a factor of depth. My device 7 cannot start until and unless device 6 has given me its share of the forward pass of microbatch 0. In this case, that is not the same because this overall depth has been cut by 2. So that factor now becomes pp, or like the number of devices p minus 1 by 2. Like this would be the bubble fraction from zb1p was p minus 1 into f plus b minus 2w. Here for both DualPipe and DualPipeV, we get that factor to be around half of that value. That is the biggest win. Of course, the parameters per device has become twice now. And like as I said, only in GPipe and naive implementations of pipeline parallelism, my activations per device scale with the number of micro batches. Otherwise, they scale with the depths or the number of stages. Now I'm on the original CAI Labs blog on DualPipeV. They wrote the title to be DualPipe could be better without the dual. And why is that? We'll think on this direction. What they suggested that this entire representation of two models, like the inputs would be on different ends and moving the weights and the forward passes and the backward passes, this can be replicated with just half the devices. What you can do, you can just flip this over or mirror this up. The better image would be this. Now, how is that happening? If I was thinking about DualPipe, I would have the same model copied twice, just in the opposite directions, right? The inputs would feed from here on this model 1, and the inputs would feed from the down to up direction for this model 2. This would have been a different batch, and I move in this direction, and this would have been a different batch, let's say 10, moving from this. The forward passes would have continued. What they suggested, I just mirror this out. The mirror would look like this V. I have just put the entire same model, but these layers or these subparts of the models would reside on the same device. And this is how it's gonna look like, cut in half. So device 3 would have the two parts like actually together, and the inputs would move in this direction. There won't be any communication from 3 to 4 because we are on the same device, and everything would continue. The final schedule would look something like this. Now, when I say 0, 0, 0, 0 on the black and in the white, this is actually now I have done the forward pass. This is not the complete forward pass. Till here, I have only like moved till 50% of my model. To actually complete the forward pass and do my loss calculation, I have to move till here. Otherwise, this would have gone in this direction, and this would have been another micro batch moving from model 2, model 2's input end. And this is how the entire DualPipeV looks like. Of course, in implementation, it's comparatively harder. So I've made a small repository called distbook, where I've written all pipeline parallelism algorithms from scratch. And they're simplified versions where you can just go through it, read it out. How do I actually carry out the weight gradient calculation and input calculations? There is another part in DualPipe which is overlapped forwards and backwards, which I haven't covered here because this is actually beneficial with EP or expert parallelism communications. So I haven't covered expert parallelism here because it requires a video of its own. And I guess that's totally it about DualPipe.
Now that wraps up the pipeline parallelism section and this deep dive on distributed training. I have tried to cover almost everything in distributed training, at least superficially, except expert parallelism, which deserves its own videos. I'll probably do that next. I am definitely not the best explainer. I just really like to talk about stuff, and I record these videos really late at night, so some mistakes might pop up. Please let me know about them in the comments, and I'll see you in the next video.